Hello, this is Team CH4. Welcome to our final presentation for the 2026 Build a CubeSat Challenge. And our CubeSat is called the QuarkSat. I'm Aiden.
I'm Zaray. I'm Karan.
Unfortunately, one of our members, Christos, is sick and therefore he is unable to present here with us today.
Here is a quick overview of our final mission. Our mission is to examine meteorite impacts on the moon's south pole and to determine and analyze the frequency of meteorite impacts for future moon bases for 3 years. It will be mostly conducted in the lunar south pole region, specifically at the 9 possible locations for the Artemis landing site. As the QuarkSat is orbiting around the moon, which we will go into detail in our orbit slide, it will take pictures of the landing sites. As for how, our QuarkSat will image the surface of the moon to detect new craters.
Our QuarkSat as a system is relatively simple, consisting of a Raspberry Pi at the heart and CNDH connecting to a IMU antenna and camera. The power subsystem, which provides continuous electricity, consists of a solar panel, a controller for it, and a battery to hold charge for the eclipses. When we are orbiting the moon, the QuarkSat will take 3 end-to-end pictures on the Artemis area of interest on the south pole of the moon once every orbit. The data then shall be compressed and sent to one of 3 ground stations on the Earth for processing.
We will show a complete QuarkSat operation in 5 steps. These 5 steps are powering up, imaging, image analysis, battery, and transmission.
First, we show the QuarkSat powering up. In this demonstration, the QuarkSat shall power up before being put into orbit, where it will then switch into autonomous mode and conduct the rest of the steps autonomously. Specifically, a person shall manually turn on the QuarkSat while in the presence of light, in the red, blue, and green LEDs are observed, before being put on the rocket to go to orbit. From power on, the CubeSat shall start itself and all of its subsystems.
Second, we have the battery demonstration. In the following demonstration, the QuarkSat shall charge itself using its solar panels when facing the sun. We have set it up so that the QuarkSat shall be exposed to sunlight while the presence of flashing green lights, the indicator of the charged battery, are observed and recorded.
Third, we have imaging. In the following demo video, the QuarkSat shall take multiple images of the moon's lunar surface at the same location each time, simulating an orbit where an impact occurred. The QuarkSat shall take a clear picture of a marked lunar surface, wait, and then take another picture of the same lunar surface with a new crater next to the first picture. The demonstration will prove that the QuarkSat is able to take photos frame to frame to image the South Pole, allowing later image alignment and pixel analysis of the frequency of impacts on the South Pole. So now, we have taken the photo using the CubeSat, and the processing will be done on the ground station for efficiency. Here's the 2 images side by side. As you can see, image number 2 has a new crater, where image number 1 does not.
Up next, we have a transmission demo, including ground station operations and radio frequency transmission.
In this video, the QuarkSat shall, using solely Bluetooth, transmit a compressed demo image to a model ground station roughly 10 feet away. Our demonstration will prove that our QuarkSat is physically able to transmit to a simulated ground station in the S-band frequency range using Bluetooth, allowing the successful retrieval of data and mapping of the lunar surface. In the next slides, we will prove, using our link budget specifically, that the QuarkSat is theoretically able to transmit data to a location roughly 384,000 kilometers away.
The CubeSat shall use connections from the ground on the Earth to the Moon in order to send data it has. Now, the CubeSat has connected to the Earth station, and we move it over to the Moon. The CubeSat on the Moon has now sent the data, and we have received it. I'll just unpack the data, and we'll be good to go. Extract all. And boom, we have our image sent from our CubeSat via our radio waves. We already answered that practically, yes, we can send data in S-band. However, we need to show that this holds for lunar orbit, given reasonable assumptions. Our link budget proves this. We used 3 ground stations to provide the maximum coverage for our QuarkSat. We selected the lowest S-band frequency for our uplink frequency because it is a more power-friendly option while still being in the S-band range for the ground stations to pick up. The antenna diameter was found on the ground station website. The aperture efficiency we figured out using the game to aperture formula. We also got our uplink and downlink frequencies from official NASA documentation. Similarly, we used a mathematical formula for the uplink antenna power at the feed and the satellite uplink GT ratio. For bandwidth, we started at the max bandwidth and decreased it until the uplink carrier to noise ratio was acceptable and the bandwidth was compatible. And we compared the link budget at different parts of the orbit. Non-diplexed, as shown on the slide, means that it does not send data at the same time it receives data. Link budget clearly shows a positive carrier to noise ratio, including a good margin, which means that we are able to transmit data at lunar distances.
Similar to the uplink, we used similar methods for the downlink values. We used a link budget calculator online for both uplink and the downlink. Lastly, we have the pixel analysis video conducted by the ground station. The demo consists of the ground station conducting image alignment and pixel analysis. The ground station shall use the 2 images of the lunar surface in demonstration 3 and conduct homography pixel alignment to align the 2 images. Then, using a Python program, detect any pixel changes between the 2 images and output an image detailing where the differences meteor impacts are. The demonstration illustrates that the ground station can compare multiple images of the lunar South Pole and analyze the frequency of meteor impacts on the South Pole through spotting new meteor impact pixels in the images.
Here we have 2 images that have been taken by our CubeSat from its various orbital excursions. Now we have a problem. We want to compare these images, but they are ever so slightly misaligned in both color, as you can see this is much warmer than the other one, and in physical alignment. But we want to find the differences. So the solution to this is a combination of sift, flan, and homography. Essentially, what it does is it finds key points in both images and merges them together in order to warp one image to fit on top of another, so we can do pixel by pixel analysis. We also change the brightness of each image to correspond to the other in order to minimize error. So I'm going to run the code now. Now that the homography has been completed, we now have our warped image 1. As you can see, it fits well with image 2. And we have our visualization of the differences. As we can see, there are a few false positives, as we will mention on our error section. These can be simply excluded in the end result. But we can see that finally our main difference has been spotted, and we can use this to gather our data.
Here is the pixel analysis in comparison to the images taken in step 3.
We tested the discharge rate of our satellite in normal operations, meaning a 120-minute stretch of suboptimal sun followed by a 13-minute eclipse period. On the graph, the eclipse period drops off steeply, showing that our solar panel was in fact generating a significant amount of solar energy. However, the solar panel is simply too weak to sustain the CubeSat, as we will explore later. In addition, we also conducted a ground sample distance demo. We created our own GSD testing board specifically for the demo, and while putting that up against the wall, we slowly moved the CubeSat backwards while it was capturing a video of the board in order to gain references to calculate the GSD. We used a formula for distance to find the distance between the camera and the paper, yielding to 1,300 millimeters. Our ground GSD is calculated from the real size on the paper and the pixel width in the photo, as we calculated that 15 pixels represents 5 millimeters, so the ground GSD was 0.33 millimeters per pixel. Using a scale factor found by dividing the orbital height by the ground tested height, we scale our ground GSD to orbital GSD, yielding 41 meters per pixel. In conclusion, we calculated that our GSD is 41 meters per pixel, which satisfied our SMART goal, in which we wanted our GSD to be below 50 meters per pixel.
For our power test, the red, blue, and green LEDs were all set to light up, indicating that our subsystems are able to light up and maintain proper function. In our power demo, in less than 1 minute after exposing the QuarkSat to sunlight, the green lights indicating the charging of the battery started flashing, indicating that the QuarkSat is able to maintain critical functions because it is able to charge and power itself autonomously. For imaging, the QuarkSat was successful in taking 2 clear images of the mock lunar surface, allowing the ground station for pictures to analyze and determine the frequency of meteor impacts. In the transmission demonstration, the QuarkSat successfully transmit images to a ground station, allowing the ground station to function like mentioned above. In the data analysis demo, key pixel differences between the 2 photos were able to be detected, allowing users to detect the presence of new craters on the moon.
Because of time limitations, we could not improve our false positive rate. We see that as negligible as for the time being, as there will still be a human analyzing whether the false positives are real craters or not. If we had more time to improve upon our final project, we'd set reducing the amount of false positives as our utmost priority. Additionally, the solar panel that was provided was too weak to sustain the Pi even at idle levels. The Pi had to be on in order for charging to occur, so we could not simply turn it off. This could cause our QuarkSat to power off during one of our tests, therefore affecting the outcome of our demos. We also had some other issues, such as the homography, which we were directed to use, does not work in the 3D curvature of the moon.
In order to scale the QuarkSat prototype, several changes will need to be made. First off, an aluminum shell shall be added to the QuarkSat to protect the components of the QuarkSat from the harsh conditions of space. The aluminum shall receive allodyne coating to prevent vacuum welding. The QuarkSat shall also have a heating and cooling system in order to keep the components, especially the battery, in a reasonable temperature range, as it will not change or discharge after a point. The QuarkSat shall also have thrusters for the orbit insertion and reaction wheels for altitude control. It shall not, though, have magnetorquers, because the moon's electromagnetic field is too small for them to be of any use. All electronics shall be upgraded to radiation-hardened components, because the moon lacks a large enough atmosphere to provide any meaningful protection from the sun's radiation. In addition, due to our findings from the previous slides, the solar panels must also be upgraded to provide adequate power to the system.
As explained before, our operation site is near the south pole of the moon, specifically between 90 plus minus 6 degrees latitude. The reason why we did not use an NRHO eccentric orbit was because we were concerned that the QuarkSat would go too fast, which affects image quality. We achieved our orbit through a paper by the AIAA, which lists multiple orbits that are most stable in a 3-year period, and we found an orbit from the paper that suits our LLO nearly circular orbit. After we settled on the orbit, we ran simulations and other tests in SDK and verified that it could stay in the orbit for the full 3 years of the mission.
We learned that coding requires much more testing and researching than the actual hardware of the CubeSat. We also learned that parts, especially the acrylic parts, require a lot of care when handling. Finally, we learned how to choose an orbit and the several different factors which go into it, such as GSD. The key takeaways from these points are that future missions should use their time wisely in order to finish and be able to perfect their project. The QuarkSat should also be tested frequently in order to catch bugs early. Finally, future missions should use resources such as papers on the matter they are researching.
Thank you for listening.